Hi everyone, here we're going to look at some additional properties of logarithm. First of all, when you take log of a product, it becomes the log of the sum. So the log of product becomes the sum of the logs. The quotient of, log of quotient becomes the difference of logs. And y raised to power x becomes x times y log base a of y. This is essentially just the product rule. Okay, so what this product rule says is that what is y to the x? That's y times, or sorry, x times, and that ends up just being log. Okay, let me write down what I'm saying. This is y times y blah 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 x times. Right? And then by this first property, this is just plus x times. Now if you add the same thing x times, then you can pretty much as well say x times that thing, right? So that's what multiplication is. It's just repeated addition. Now using these properties, let us evaluate these expressions. Log base 42 plus log base 432. So I notice first of all, the base is same, which means I can use my property, and this becomes 2 times 32 if I use it in reverse, which then becomes 64, which then becomes 4 cubed, which then becomes 3 log 4, which is just 3. Or at this point, you can just see this is function and inverse. So we can use a previous property and conclude that this is going to be 3. Second one, again, the base is same. With the base being same, this is log base to 80 over 5, log base to 16, and 16 is 2 to the power 4. So once again, we have a function and inverse. So you can use that to conclude that this is going to be 4, or you can use the property to say this is going to be 4 log base 2 of 2, which is 1. So this is 4 times 1, which is 4. Next is negative 1/3 log 8. Now, in this case, we use this property in reverse and write this as 8 to the negative 1/3. But what is 8? 8 is 2 cubed. And then we have learned properties of exponents. So this is going to be 3 times negative 1/3. And that's just log of 1/2 or negative log of 2. So either of those are okay, as long as you get rid of this. And well, the only reason we get rid of this is because we already know that 8 is 2 cubed, which means that this thing can be simplified a little bit, right? So we kind of already know that. The next kind of problem would be expand these expressions. So here you're not solving or simplifying anything. You're simply rewriting this as log base 2 6 plus log base 2x, which can be further written as log base 2 2 plus log base 2 3 plus log base 2x. Then this is 1, and the others cannot really be simplified, so we stop right here. This would be ln of a plus ln of b minus ln of cube root of c, which is log a plus log b minus log c to the 1/3. The 1/3 carries over to get log a plus log b minus 1/3 log c. So again, for these cases, you're not, generally there will be no simplification involved other than the fact that you're just rewriting it from a product form to a sum form, or it would say combine, in which case you would rewrite it as one single term. So here, this is x cubed, and this is x to the 1/2. And then there's an addition, which means you multiply the terms, as x cubed times x plus 1 to the 1/2, which that's it. There's no more simplification that you need to do. Let's look at an example. There's something called, oops, that makes it ugly, law of forgetting. If a task is learned at a performance level P naught, then after time interval T, the performance level P satisfies this particular relation. So it turns out that after experiments, when models for how we forget things were created, it was found that we forget it at a log scale, which is kind of good because linear would be really bad. Yeah, that means you would forget things really fast. Log means the process of forgetting is not that fast. And then it was found that it satisfies this relation. Log P equals log P naught minus some constant C times log of T plus 1, where C is a constant that depends on the type of task and T is measured in months. It says solve for P. So first of all, let me rewrite. Log P is log P naught minus C log T plus 1. Now to solve for P, I'm going to rewrite this by combining them. This is going to be P naught minus log of T plus 1 to the power C, because the C jumps over here. Then this becomes log of P naught over T plus 1 to the power C, and this is log of P, which means at this point you can sort of get rid of the logs and you get P is P naught over T plus 1 all raised to power C. So that is part A. Now what is part B asking you to do? Part B says, if your score on a history test is 90, what score would you expect to get on a similar test after 2 months or after a year? Assume C is 0.2. Okay, so your test score is 90. Okay, that's our performance level. So however you're measuring a performance, in this case we will say we are measuring the performance as the score. So P would be 90 over, let's say, 2 months. In 2 months, this would be 3 to the power 0.2. So you can evaluate that value, and this comes out to 72.25. So this means that if you score 90 on this test, then in 2 months, your score is already dropped to 72.25. What about after 1 year? After 1 year, this is going to be 90 over 12 plus 1, which is 13 to the power 0.2. So let me find that. It's going to be 13 to the power 0.2, and that actually comes out to 53.88. So that's a pretty drastic reduction, right? Of course, this is assuming that whatever is on the test, you have not revisited that thing and not seen it again, worked through it, or had any discussion about it. So it was something you learned and then it's been stagnant. In that case, it's gonna decrease at a log scale level. Now, for exponents, we have the base. For logarithms, we have the base. So this base is an important thing. However, so far we have been just kind of saying that 10 is an important base and E is an important base, right? However, we also want to understand how we can go from one base to the other. So we use a base change formula. It says, if I want to write x in a base B, then I choose a base A that I know. I write it as base A, and I divide this base by the other base. Okay, so what is the other utility? The other utility of this is that then we only have to compute one set of log values. Okay, so for example, when you say log of 27.337, earlier there used to be log tables where you can find these values, right? And so the way this works is, if we have this base change formula, then you only need to have one set of log values. So even if I ask you log base 7.3 of 39.6, then I don't have to recompute that. I can just look at, say, log base 10 of that number, and I can still figure out the value. How is that going to work? Let's see. So to find log base 8 of 10, right, I am going to rewrite this as log base 10 of 5 and log base 10 of 8. Similarly, this would become log base 10 of 20 and log base 10 of 9. Now these are things which both of which are computable, both of which we know the value of because they are to the base of 10. Okay, last problem here for this video and for the topic on logarithm. Negative log of x minus square root of x squared minus 1 equals log of x plus square root of x squared minus 1. Now this is an interesting problem. There are many ways of showing that this is true. Okay, I'll show you one of the ways. Method 1 is I look at this and I rewrite this using the log property. So the negative becomes an exponent. So this is actually log of 1 over. Now, whenever you see a fraction which involves a radical, you should automatically think of trying to rationalize it. So rationalizing it would include dividing this by the conjugate, or that's the thing with the positive. When you do that, this entire expression now on the top is x plus square root of x squared minus 1. And on the denominator, that's going to be a squared minus b squared. So it's going to be x squared minus, we get rid of the square root. So this comes out to log x plus square root of x squared minus 1. X squared minus x squared plus 1 is just 1, which is what we are trying to show. Okay, while we are at it, I'll show you the alternate method. Alternate method is that let's add these together, right? So basically we reframe the question as show that this plus log of x minus x squared minus 1 is 0, right? So the proof, now I use the log property and addition becomes multiplication. Since addition becomes multiplication, now these terms are a plus b and a minus b, so they become a squared minus b squared, which in turn becomes log of 1, which is 0. So that's another way to show the same thing. You can, instead of doing the rationalization, you can just show that the sum is positive, but essentially what the inner working is the same. The inner working, or this fact, is true because when you multiply these two numbers, you get 1, or these two expressions, you get 1. Okay. All right, that's it for this video. We still have to look at a few things about solving equations involving exponents and logarithms, which is what we will do in the next one. Okay, thank you.